So the first thing is I'm assuming Rob's getting your homework. I already got the ones here. The next thing is I got a homework number 9. Last one for Tuesday the 1st. That's next Tuesday. Okay? What I wanted to do is I picked 3 problems out of this chapter 22 because there's 3 things we're going to do tonight out of here. You know the problems you just gave me. You calculated a confidence interval. You chose a sample size for a particular confidence level and margin of error, and then you did a test of significance, right? You did a confidence interval, and then there was a 4th problem you just turned in. It was something about significance levels and whether something was statistically significant. So you did a confidence interval, a sample size, and a test of significance. My 3 problems here out of chapter 22. One's a confidence interval, one's a sample size, and the other one is a test of significance. Okay? Same 3 problems. Obviously, there's going to be 3 different formulas. Okay? Now, where we're at in this chapter is this chapter 22, we're no longer looking at a population mean. Now we're looking at a population proportion. Right? And what I used on you last week was P is your population proportion. We thinking about this as some proportion of some outcome in the population. If you like, whatever that outcome is, we think about it as being a success. That's your parameter. And then we have this little p hat, which is your sample proportion. It's the proportion of some outcome in your sample, or if you like, it's the proportion of successes in your sample. So the little game we want to play here is we want to use p hat to estimate p, just like I wanted to use x bar to estimate mu. All right? I want to use p hat to talk about evidence against some claim about your population proportion, your parameter. So the mu has now become a p, and the x bar has become a p hat. Okay? So if we're going to do anything in this chapter, your statistic here is this sample proportion p hat. We got to know about its sampling distribution. And so the last thing I wrote up last Thursday is this sampling distribution of p hat. It has a mean, it has a standard deviation, and it has a shape. I am on the bottom of page 518 here. And the first thing is the mean. Look, we always use mu for the mean. I subscripted with a p hat, so you know we're looking at the sampling distribution of that statistic. Turns out to be p. Just like mu sub x bar, the sampling distribution, the mean of the sampling distribution of x bar was mu, your unknown parameter in your population, right? That's where it's centered. The standard deviation is always sigma, subscripted with the p hat. So you know we're looking at the standard deviation, the sampling distribution of the sample proportion. It turns out it is the square root of p times 1 minus p all over n. Not as clean as sigma over the square root of n, but that's your standard deviation. The third thing is the shape. And as the sample size n increases, the sampling distribution of p hat is approximately normal. Not a shock. Every distribution I ever worked with in this class eventually somehow shows up to be approximately normal or normal. So it's going to be normal. We know what it looks like, right? It's symmetric, single peak, bell shape. It satisfies the 68, 95, 99.7 rule. Approximately. So obviously, the larger your sample size, the more normal it looks. Okay? Now, I'm going to repeat myself from stuff out of chapter 16 here at this point. Excuse me, out of 15 about X bar. All right? Now, here's my deal. Number one, and here's little notes that go along with this. When I tell you that the mean of your sampling distribution is equal to the population proportion, that parameter, what I'm telling you is that p hat is an unbiased estimator of p. Which means sometimes when we take a sample and we're going to calculate this sample proportion p hat, sometimes it will be greater than p. You'll overestimate your population proportion, and sometimes it will be smaller than p. Sometimes you will underestimate. Remember, you would be biased every time you took a sample, you overestimated. You'd be biased if every time you took a sample, you underestimated. Well, no. If this sampling distribution is centered at p, then sometimes it's larger and sometimes it's smaller. Sometimes you overestimate and sometimes you underestimate. When I tell you the standard deviation of that sampling distribution is this square root of p times 1 minus p over n. The first thing I see is sigma over the standard deviation of the sampling distribution of p hat, sigma subscripted with the p hat, decreases as n increases. Now, if I could see all your faces, you can't be looking at me like you haven't heard this shit before. Those are the same two things I wrote for you back in chapter 15 when we were talking about the sampling distribution of X bar. Yes, I understand there's mu's and stuff like that, and there's different formulas, but as far as interpreting what was going on and saying something about what was going on, X bar was an unbiased estimator of mu. As I increased the sample size, the standard deviation got smaller. That's what I'm telling you here, right? The next one I'm telling you is to cut this standard deviation in half. If for some reason you want to cut it in half, you need 4 times the sample size. Because the 4 is inside the square root of 4, inside the standard deviation square root, and we know the square root of 4 is 2, so you'll cut everything in half then. Those things I have written there is the same things I told you before about X bar. Okay? Now, everything we do here in this chapter, confidence intervals, test of significance, the sample size is going to play a role here. Depending on what we're doing, we're going to have requirements on the sample size. So for all this to work, for everything to work here in this chapter 22, I'm going to give it to you like this. The first thing is, we need our sample size to be at least our population to be at least 10 times bigger than the sample size. Everything we're going to deal with is. All right? That's one thing. And then you're going to see me have little things about, okay, here's your confidence interval, here's your conditions. Here's your test of significance, here's your conditions. Does anybody know what condition number 1 is in both of these? Oh, hell, it's a simple random sample. That's been the same condition in all this stuff. It's always a simple random sample. And then number 2 is going to be, how large a sample do we need so that everything's approximately normal like we need? Okay? Now, I'm going to take them one at a time here. We're going to talk about the confidence interval, sample size, test of significance. Now, the confidence interval we're going to look at, it's called the large sample confidence interval for P. Remember, that's your parameter here. That's your population proportion. Now, here's what I want to do. I want to use my sample proportion to estimate folks, I'm using my statistic to estimate my parameter here. That's what that says. Okay? I would like to have a level C. Remember, every confidence interval has a confidence level that comes along with it. Remember, there's always a little Z star there, depending on the confidence level. Yep. For P. Now, I'm not going to go back and start drawing pictures here. Here's what I want to use. We would like to use the following. Remember, every confidence interval that we look at is supposed to be an estimate plus or minus a margin of error. Your estimate is always your statistic. I want P hat plus or minus, then I want my margin of error. And I want to use exactly the same idea that I used before. I want my little critical value, my little Z star that comes from your confidence level, and that's always multiplied by your standard deviation. Remember that was sigma over the square root of n, the problem you just turned in here about the confidence interval? Well, what's my standard deviation this time? The square root of P times 1 minus P over n. Right? We changed sampling distributions. That's your standard deviation. It looks like an estimate plus or minus the margin of error. Your estimate's your P hat, your sample proportion. Your margin of error is your little critical value times your standard deviation. All right? I'm following the same format as we had before. Same form. We have a problem. The problem is we don't know. Why is that a problem? P shows up in standard deviation. You understand, if we knew P, would we be trying to estimate it? The hell no. It shows up in the formula I want to use, the P, the parameter I'm trying to estimate shows up in the formula there. Okay. Just because we don't know it doesn't mean we're going to stop here. We replace P with P hat in that standard deviation. And again, you can't hang your head. You just can't walk away and say, what the hell is the guy talking about? Look, nobody stopped me here when I wanted to use P hat to estimate P. So why would you stop me in using it in there? You're not, right? If P shows up there, hell, just estimate it there. Now, the catch is this. When I do this little part here, when I use this P, when I replace P with P hat in that standard deviation, there's something called the standard error. And it's this right here. When I try to estimate P with P hat, that's no longer the standard deviation. That's called the standard error of P hat. Because not only now are you estimating P just straight up, you're estimating the mean of this sampling distribution, you are estimating the standard deviation of this sampling distribution with what's called the standard error of your statistic, the standard error of P hat. The reason it's standard error is because you're estimating the standard deviation. Okay? Now look, folks, that's a gigantic step. Oh, we're estimating shit all over the place now. Not a shock. We're at the end of the semester. We're estimating stuff everywhere. So, if I'm allowed to do that, we got no other options. That's what you do. When you don't know something, when you don't know some parameter about a population, what do? You take a sample, you calculate the appropriate statistic, and you use it to estimate that parameter. That's what the hell we're doing here. Okay? So, my confidence interval is going to end up being this. Oh, you stick the standard error in for the standard deviation. That's our confidence interval when you're trying to estimate a population proportion. The Z star comes from the confidence level. The P hat comes from the data, right? That's your sample proportion. That's the proportion of successes in your sample. Okay? Now, notice this looks like an estimate plus or minus a margin of error. Just like I told you, every confidence interval in this class would look like. Something to estimate. The estimate's always your statistic. Plus or minus a margin of error. A little bit different here because that's not the standard deviation. That's that standard error we talked about right there. Okay? That's my confidence interval. I got a formula. It's on your formula sheets. You don't memorize that shit. What you ask yourself is the question asking me to estimate a population proportion? It is. That's my guy. Go find it on my little formula sheets there. Okay? Now, you're allowed to use this. 1. Here are the conditions to use that large sample confidence interval. 2 is about sample size. What I need is, I need n times p hat to be bigger than or equal to 15. And I need n times 1 minus p hat to be bigger than or equal to 15. I'm giving you the formulas here what to check. The book doesn't do that. They give it to you in language here, and this is the number of successes in the sample. When you look at n times p hat, when you look at the sample size times the sample proportion, that is the number of successes that's in your sample. It needs to be bigger than 15, bigger than or equal to 15. Down here, look, if p hat is the sample proportion, is the proportion of successes, what's 1 minus that? That's got to be what I consider a failure, right? Your outcome's either a success, the one you're looking for, or it's one that you're not looking for, and it is a failure. So this is the number of failures in the sample. There's your confidence interval. There's when you're allowed to use it. So, what I want to do here is I want to find us a problem. Yeah, I know there's an example, 22.4 here. You can read that. I'm going to come over here to page 523. And I want to look at 22.5. Okay? I'm going to do this to you every problem tonight. I'm going to go through and I got a problem for us that, okay, here's where you start from scratch. 22.5 says Canadian attitudes towards guns. Canada has much stronger gun control laws than the United States, and Canadians support gun control more strongly than do Americans. A sample survey asked a random sample of 1,505. There's your sample size. There's your random sample of adult Canadians the following question. Do you agree or disagree that all firearms should be registered? Of the 1,505 people in the sample, 1,288 answered either agree or agree somewhat. So 1,288 agree in some form. That's your successes here in the sample, right? That's the outcome you're looking for, that they said they agreed. Whether they agreed strongly or agree somewhat, they agree. Okay? Now, Part A says, the survey dialed residential telephone numbers at random in all 10 Canadian provinces, omitting the sparsely populated northern territories. Based on what we know about sample surveys, what is likely to be the biggest weakness in this survey? What's the problem with their sample? Well, first off, they threw out the Northern Territory. Don't you think there are people there who've probably got opinions about this? Yeah. They're dialing phone numbers. What's wrong with that? What about the people who don't have a phone? We leaving them out? What about the people who only have a cell phone? We leaving them out? Yeah, so your biggest problem with all this is, to give you a term from before, you got a problem with undercoverage here. When you're looking at just using house phones, home phones, your sampling frame is incomplete. You got a problem with undercoverage here. Not only did you leave out one territory, but you left out everybody that doesn't have a phone or uses only a cell phone, that doesn't have a home phone. Your problem here is you're suffering from undercoverage. Now, how do I feel about everything other than that? Okay, I feel okay, but you got issues with the data here. Okay? Now, Part B. Nonetheless, act as if we have an SRS from adults in the Canadian provinces. Okay, so they're telling me you got an SRS. That's good. Okay. And then give a 95% confidence interval for the proportion who support registration of all firearms. So, Part B, we want a confidence interval. Your confidence level is 95%. I know if I want a confidence interval and the confidence level is 95%, my Z-star is 1.96. It comes off Table C in the back of the book. You may have done enough problems now you got it memorized. Okay. I need to find my sample proportion, my p-hat. My p-hat is always the number of successes, the number that agree, divided by your sample size. You punch that in the calculator, and I get 0.856. Now look, normally when I'm working with things in this chapter where it's all about proportions, I usually give myself 3 decimal places just to be sure. Okay? Now, I know the formula I want. I want to estimate P. I want to estimate the proportion of all Canadian adults that would agree with the registration of all firearms, right? That support the registration of all firearms. Now, I'm looking at all Canadian adults, right? That's your population here. I know I'm trying to estimate a population proportion, so my formula is P hat plus or minus Z star square root P hat 1 minus P hat all over N. Now, at any point, you can do the little pieces, but I'm going to do the same thing as I've done to you before. I'm going to work from right to left. I've got 0.856 plus or minus 1.96 square root. Now, I always do this. P hat is 0.856. 1 minus that is 0.144. Your sample size here is 1505. All my numbers came from the problem. They didn't give me the sample proportion. They gave me the number that agreed, that said, here's the success. 1288. 1288 divided by 1505 is the 0.856, and I'm plugging it in everywhere. Now, we do a little piece at a time. And what I mean by a little piece at a time is 0.856 plus or minus 1.96. If you pull the calculator out and you take the square root of 0.856 times 0.144 divided by 1505, the square root of that whole stuff that's on the inside, you get 0.009. I'm not going to stand here and tell you how to punch it in the calculator because it depends on your calculator. You've got to figure out how to work the calculator on your own. The square root of that part right there gives me 0.009. In other words, what I'm telling you is the standard error here, right? The standard error, the estimate of your standard deviation is 0.009. That gives me 0.856 plus or minus, multiply 1.96 times 0.009, and I got 0.018. There is your confidence interval. There is your estimate plus or minus your margin of error. Your margin of error here is 0.018. So, just to continue, when we add, remember there's 2 pieces. When we add here, I got 0.874. When I subtract, 0.856 minus 0.018. I get 0.838. Now, at this point, that's your confidence interval. I'm going to write it for you like this. That's 0.838, comma, 0.874. Remember, you're giving me an interval on the number line. It's always the smallest first. Now, you do realize that nobody wants to read your proportions, right? (83.8%) to 87.4%. I moved the decimal place 2 to the right. People like to hear about percentages. So my confidence interval here, this 95% confidence interval for this population proportion is 83.8% to 87.4%. I don't know what it's going to show up like. When you give me the problem, I'll read either one. I don't care. I don't know what the answer is going to show up like on the final. I'm giving you both of them, right? If it's percent, give me the one on the right. If it's the other one, give me the one on the left. Proportions. Now, I know not every time they ask you a question in the book do they ask you to interpret this. In other words, give me the language. What's the language here? The language is, I'm going to change it a little bit. You know, normally I say we are 95% confident, right? Another way to say the same thing is with 95% confidence. You just give everybody your success rate. The true, now at this point I can put proportion or percentage, depends on which interval you want to use. I'm going to say the true proportion of, now what group of people, what's our population here? What are we talking about? Of Canadian adults that, and what are we looking at here? It's gun registration, right? Adults that support registration of all firearms is between, what is it, 0.838 and 0.874. You give me your success rate. You tell me what the hell we were trying to estimate. Then you give me the interval. If that didn't say proportion, it said the percentage, you would give me 83.8% and 87.4%. Depends on how it's worded. There's no magic here. The interpretation of things is exactly the same. Yeah, I understand. There's no mean here, right? There's no mu, there's no averages, there's no X bar, there's none of that shit. There's a sample size and then there's a number of successes. That's it. That's where I get the p hat, and then I'm plugging everything into my formula. Okay. Problem number 2. That's your confidence interval. It doesn't matter which one we pick out. Look, I did 22.5. You're going to do 22.6 for me for homework? Okay, instead of talking about Canadians and their attitudes towards gun, we're talking about weightlifting injuries. There's going to be a sample proportion. You'll plug it in, get me the confidence interval. Okay? The next thing we want to be able to do is choosing the sample size. Okay. We fix the confidence level and margin of error. Just like before. right? Remember before, somebody wanted you to choose a sample size because you wanted to calculate a confidence interval. You want to do it at this confidence level and you wanted to produce that margin of error, and we had a formula for choosing the sample size that would do that, right? I want to do the same thing here. Now, in my little formula for my confidence interval, remember it's an estimate plus or minus the margin of error. The margin of error I used M on you before. That's your margin of error. That's the plus or minus part. Is this right here? Your Z star times your standard error. Okay, we got a problem again. This is my last problem for tonight. What I mean is, this is the last time I got to say to you, look, I'd like to solve for n here and everybody would be good. But you see that margin of error. It involves p hat, correct? When do you get p hat? It's after you've taken your sample and you had the number of successes divided by your sample size. You're trying to figure out the sample size before you ever took the sample, correct? You're not going to know p hat. So, problem. We don't know. Remember, this is before the sample is chosen. You're trying to figure out what sample size to take. Okay. We could punt and say, heck with it. I don't want to do a sample size. We don't know this. Nah. Make a guess. Call it. That's P star. Now, when I say make a guess, you're not closing your eyes and making a guess. I'm going to tell you how to make your guess. I can't say estimate, right? We're going to make a guess at it. We're going to estimate p hat. We're going to do some educated thought here. Okay? Now, I got two ways to get p star. Your guess for p hat. Use the results of a previous survey. Maybe somebody else took a sample and asked the same question you're interested in. Or a pilot study. Take a small sample and see what the proportion of successes is in the small sample and use that as your guess. 2. Use P star equal to 0.5. Go dead in the middle, right? P star, your P hat's going to be between 0 and 1. Go right in the middle. Right? Use it 50%. Okay? This is conservative. That's what you would read in your book. Oh no, when you use that right in the middle, that 0.5, this is a conservative guess. What that means is, when you take the sample, of size n that you get from using P star equals a 0.5 and calculate the confidence interval, your margin of error will be smaller So in a sense, using P star equal to 0.5, going right in the middle between 0 and 1, will produce the largest sample you need to ensure that your margin of error is what you said it was. After you've actually taken the sample of the size you would get, okay, and your little p hat turns out to be anything other than 0.5, your margin of error will be smaller than what's required and everybody will be happy. Okay? Now, when is it safe to use this? When should we be thinking about a pilot study or some previous survey? Use P star equal to 0.5 when we expect your sample proportion to be between 0.3 and 0.7. In other words, if you're going to be close to 0 or you're going to be close to 1, you better be looking for a pilot study or some other previous survey. Okay? Now, you don't get to make this choice. If the problem doesn't tell you to do something, is it doesn't tell you to do this or it doesn't tell you to use that, you use 0.5 and we go on about our business. If it tells you to use this number here, this pilot survey or this sample survey for your little guess, you use it. Now, the formula that we are looking at here for the sample size is this is my margin of error. And I'm going to stick that little P star in there. You know, where we're going to use 0.5 or some pilot or previous survey. If you solve for n, this is not an algebra class, folks. I get n is equal to z star over m squared p star times 1 minus. That's your formula. That's the formula that shows up in page 524, sample size for desired margin of error with a given confidence level. It's on your formula sheet. So what you have to ask yourself, is the problem asking me to choose a sample size where I'm trying to calculate a confidence interval for a proportion? Yes, that's your guy. Right here it is. Okay? So we come over here. You're going to do 22.8. I'm going to look at 22.7. I'm on page 525. It says, the Monterey Bay Aquarium, founded in 1984, is situated on a beautiful coast of Monterey Bay in the historic Cannery Road District. From 2009 to 2013, the aquarium conducted a survey of a random sample of visitors as they exited the museum. Random sample, that's good. The survey includes visitors' demographic information, use of social media, and opinions on their aquarium visit. In 2013, the survey included 165 visitors. That's your sample size. Of which 42 used a mobile device such as an Android phone or an iPad during their visit. What is that? What was the number? 42? Used a mobile device. Okay. That must be a success. That out of that 165 people that were 65 or over used a mobile device. That's what we consider. That's the outcome we're looking at, that they used a mobile device. Part A says, what is the margin of error of the large sample 95% confidence interval for the proportion of visitors over 65 who used a mobile device during the visit? Now you understand, that's the P, right? The population proportion you're looking at is the proportion of visitors over 65 that used a mobile device during their visit. That's your population proportion you're interested in. That's what your sample is. It's people over 65 that were at the aquarium. Okay? So I want the margin of error. Well, we're supposed to know the margin of error is this. Yeah, this shows up as part A. This is not a sample size one. They want the margin of error. For what was the confidence level here? It says 95%, that large sample one. We know Z star is 1.96 off of table C in the back of your book. Okay? Now, what do I need to know here? I need to know p hat, right? I need to know the proportion in that sample of 165 that had used a mobile device. So my p hat is, what was it, 42 over 165. And I get a sample proportion of, I got 0.255, 3 decimal places. Okay? So my margin of error is going to be 1.96 square root 0.255. 1 minus 0.255 is going to give you 0.745 over your sample size is 165. You pull out your calculator. The margin of error is 1.96. And for your little standard error, remember that p hat, 1 minus p hat over n, square root of that, that's your standard error. I got 0.034. I'm doing them in little pieces. Your margin of error here is 0.067. That's what it asked you for. Practice a little bit more getting the margin of error. What I'm interested in here is Part B. Part B says, how large a sample is needed to get the common plus or minus 3 percentage point margin of error. You want the margin of error to be plus or minus. You can't use 3%. You've got to turn that into your decimal, plus or minus 0.03. Things are usually given to you in terms of percentages here, but everything is calculated and done in terms of proportions. Move the decimal place. Okay? The confidence level we were looking at was, remember, that was 95%. My little z star was 1.96. Now, I'm going to read the last sentence here because I need to know something. It says, use the sample from Part A as a pilot study to get P star. What they're telling you is use P star equals 0.255. That's what they're saying. When they say, use the sample from Part A, use what that little pilot study of 165 in Part A as a pilot study to get P star. The reason they're doing that is, you see that little P star is 0.255? Why wouldn't we want to use P star equals 0.5? You expect it to be between 0.3 and 0.7? Not based off of that one. So we're going to use that as our little P star, as our guess here. So my sample size is supposed to be 1.96 over 0.03. We don't throw in the plus or minus part. I just write it like that so you know you're looking at plus or minus 0.03 as your margin of error, right? The margin of error is 0.03 and you add and subtract. Times, what is it, 0.255. 1 minus that is 0.745. Don't forget to square that 1.906. 1.96 divided by 0.03. You punch all that in the calculator. And what you get is n is equal to 810.9. So what do we do about that 9/10 of a 65-year-old person? What are we going to do about that? What do we always do on sample sizes? We always round up. Take n equal to 811. Always round up. Yeah, I know, not a big deal. You're going to round 810 to 811 anyway. But if that was 810.01, you'd still take 811. That's number 2. It's still the formulas, right? It's like you got to know you're looking at a proportion. So we got the confidence interval, you got a sample size. How you get that little guess, how you get that little P star, the problem told me there. If the problem hadn't told me to use that as a pilot study, I would have used P star equals 0.5. Okay, with everybody, right? If nobody tells me anything to use this or use that or consider that pilot study, I'm using 0.5. That's the way it works. Now, the third thing we want to do is significance test for a population proportion P. Okay. There's 4 steps here. State the hypothesis, calculate your test statistic, find your p-value, state your conclusion. There might be a fifth. There's a significance level, compare your p-value to that, and then tell me whether things are statistically significant or not. Well, in this case, the null is your population parameter is not a mu, it is a p. And it's going to be equal to some fixed value that comes out of the problem. All right. The alternative has 3 choices: greater than, less than, or not equal to. Whatever that little p naught is, it stays in the alternative 2, just like before. I'm changing the letters on you folks. Okay? Now, my test statistic is still a z-score. The z-score is, you're going to have a value, you're going to have your sample proportion, you're going to have a value that you're interested in, minus the value that's in the null. That's the mean of your sampling distribution. You're assuming where that sampling distribution of p hat is centered. And then you're going to divide by, the standard deviation is going to be square root p naught times 1 minus p naught over n. Look, this value right here is showing up all over the place there because we assume the null hypothesis to be true. Now, I'm on page 526 in your book. I'm not going to write the rest of this box down because the 3 pictures there, where the first picture is you're looking at a one-sided test to the right. The second picture is you're looking at a one-sided test to the left. The third picture is you're looking at a two-sided and you're going to double whatever's in it. Those are the same 3 pictures out of chapter 17. In other words, the p-value has the exact same interpretation here as it did previously, as in the problem you turned in for homework. All right? The only other thing I want to say here about this, when am I allowed to use this test? Anybody know what number 1 is? It's always a simple random sample. Now, number 2 is sample size. And the sample size is this. A little different this time. N times P naught. Remember, that's the value that shows up in the null. That's the value that we're claiming to be true about the population proportion. And N times 1 minus P naught needs to be bigger than or equal to 10. Now look, when I gave you that for the confidence interval, that was the number of successes and the number of failures in the sample. Here, this is not the number of successes and the number of failures in your sample. It is the expected number of successes and failures in your sample if the null hypothesis is true. Right? That's the P naught. That's the value in the null there. Now, we need a problem. Oh, I know, I'm rolling right along. And it's because at this point, what's changing here is how do I calculate the z-score? In the confidence interval, how do I calculate the confidence interval? What's the formula? The interpretation is the same, right? Now, what I want to do is this. I gave you problem 2210, right? Was that what I gave you to do for a test? That's your test of significance here on page 528. I found one that I wanted to do, and I want to look at 2237, and I'm on page 535. Okay? I didn't like the other two that was around 2210 that was back there, so then I went to this one. It says, a high school teacher in a low-income urban school in Worcester, Massachusetts, used cash incentives to encourage students' learning in his AP statistics class. This one also caught my eye because the guy was paying them off, right? So I thought that was kind of cool. It says, in 2010, 15 of the 61 students enrolled in his class scored a 5 on the AP exam. Nice. So you're looking at a sample here of 61, and you had 15 that made I'm going to say scored a 5. The success is that the student scored a 5 there. So your sample size here is 61. It says, worldwide, the proportion of students who scored a 5 in 2010 was 0.15. In other words, there must be around 15% worldwide that scores a 5. It says, is this evidence? What do they want me to do? Hell, I ain't even going to read the rest of it. You see the word evidence. Is this evidence? They want to test the significance here. Is this evidence that the proportion of students who score a 5 on the AP statistics exam when taught by the teacher in Worcester using cash incentive is higher than the worldwide proportion of 0.15? Look, they got to be real specific here. Your sample is from Worcester, Massachusetts, taught by this one teacher that was paying them. So does that mean that, I get the students in Worcester to take this professor, the teacher, and he pays them? Or are they going to do better than the average students worldwide? All right? If I flip the page here, it says, state the hypothesis, find the p-value, and give your conclusions in the context of the problem. Do you have any reservations about using the z-test for the proportions for this data? Well, I'm going to assume that this part, that's a little questionable. No, can we consider this a simple random sample of all the students? No, it looks like he'd done this one time, so that's a little question. I'm going to put a little question mark there. You know this little n times p naught, which is 61. I'm going to come back to this in a moment. And then this n times 1 minus p naught, which is 61 times something. I'm going to come back to there because I don't know what value I want to use for the null hypothesis yet. Okay? Now, I'm going to give you 4 steps here. Like I said, I promise you, we'll come back to this. That's 1 and that's a 2. If I state the hypothesis here, the null is p is equal to, what was it? 1. And then the alternative is just p. Before I wrote a mu there. When you're trying to make claims about a population mean, you're making claims about a population proportion. I'm going to back up here. The question says, is this evidence that the proportion of students who would score a 5 on the AP statistics exam when taught by the teacher in Worcester using cash incentives is higher than the worldwide proportion of 0.15? The alternative is, what you're looking for evidence is that p is greater than 0.15. That means the null is equal to 0.15. 2, your test statistic, your z-score. Your z is going to be, what's my p hat value here? Do I have enough information to find p hat? I'm going to scroll back up. I got 61 students. 15 of them scored a 5. There's 15 successes out of 61 students. My p hat is 15 divided by 61, and I got a 0.246 is my sample proportion. 24.6% of this teacher's students that he was paying got a 5 on the AP statistics exam. Okay? So, I'm supposed to have my p hat minus my value in the null divided by the square root, the value in the null, 1 minus that, over your sample size. I plugged right into that z-score I had on the previous page. Now, I do this a little piece at a time. I got on the top, I got 0.096. There's just too much crap going on with the formula at this point for me to do it all at one time. So I gave you 3 decimal places in the one on the top. If you take that square root of 0.15 times 0.85 divided by 61, you get 0.046. I rounded the 3 decimal places. Then when I do this division, I get 2.09. Is that small or large z-score? I mean, it's not huge, but it's rather large. Are you expecting a small p-value or a large p-value when you got a large test statistic? I'm expecting a small. Remember, they go opposite of each other. Okay? 3. Here's your standard normal. Remember, that's where z-scores live. Standard normal. I label it for you. The mean is 0. You got a z-score of 2.09. What area do you want? You want the area to the right or you want the area to the left? That's telling you to look to the right, greater than, right? So I want this area. You go to Table A. I'm going to go to the row that's 2.0. The column is like you've done at least 10 or 20 times before now. When you look up that area, you're always looking to the left. The area I got to the left was 0.9817. Is that correct, Marcus? And then that means this area to the right is 1 minus that. I got a 0.0183. Your p-value here is 0.0183. Is that small or large? Okay, you got a small p-value. What do we want to do? In general, I would like to reject H naught in favor of the alternative. Right? Small p-value, right? You want to get rid of the null, you want to favor the alternative here. What does that mean in the context of this problem? What do I got strong evidence? I got strong evidence in favor of the alternative here, right? I got strong evidence. That the proportion is greater than 0.15. Now, I just wrote proportion this time. I didn't write the whole spiel about what are we looking at. Well, we're looking at the proportion of students taught by this teacher that was paying them off in Worcester, Massachusetts. That's what you're looking at. That is, we got strong evidence that the proportion of all the ones that we would do like that would be greater than 0.15, or the percentage is greater than 15%. All right? Now, I worked the problem through, right? I state the hypotheses, calculate the z-score, test statistic, find the p-value off the standard normal table A. Small one, okay. You got strong evidence to favor the alternative here. Now, I want to go back up the page for a second because there's some issues with this whole problem. That's one of the other reasons I picked it. Not only the fact that the guy was paying him off, or the lady was paying him off, but the value that's going to go in here is 0.15. The value that's going to go in here is 0.85. Remember, that's the value that shows up in the null. That's that little piece of naught. If I do that, this turns out to be 9.15, and this is 51.85. You see that? That's less than 10. That's an issue. That's a little flag here. First off, I don't see simple random sample. My expected number of successes and failures in your sample if H naught is true, right, are not both bigger than, this has got issues all over the place. Even though we went ahead and worked the problem, I didn't see anything about random sample. I didn't see anything about an SRS, and then I'm a little less than 10 here. Things aren't going to be as accurate as we like. Okay? The last question here says, does this study provide evidence that cash incentives cause an increase in the proportions of 5s on the AP statistics exam? I'm going to read the magic word to you again. You see where it says cause? Is this cause and effect? How do we know about cause and effect? Does anybody see randomized comparative experiment here? Did we have a group of them that got paid and a group of them that didn't and we checked them? No. There's no cause and effect here. You got evidence that supports that, but it's not saying it causes, right? It doesn't say paying them off causes them to do better. Everybody look at me for a second everywhere. A couple Thursdays from this coming Thursday, when they start asking you shit about, you see that right there? Does this cause that? You better ask yourself, anywhere in this problem, did I read anything about doing an experiment where we imposed the treatment and we had these groups and we compared them? That's the only way you know cause. Cause and effect. That's what they're asking you here. Yeah, I know. We're in chapter 22 and all of a sudden somebody's asking about cause and effect. That's what it's asking you. Does this study provide evidence that cash incentives cause an increase in the proportion of 5s on the AP statistics exam? I don't know. Hell, this looks like some kind of observational study to me. We just observed this one class. We need to do a randomized comparative experiment. You cannot come up with cause and effect unless you have a randomized comparative experiment. Everybody understand? Okay? That's the deal here. Now, those are the problems that we need to be able to do in this chapter. Confidence interval, you got a formula. Sample size, you have a formula. Test of significance, when I say you have a formula for the z-score, the test statistic. Everything else is the same. All right? Now, here's my thought. That's the last chapter I'm doing any of this. From now on, you're going to see me click in and interpreting. Right? I mean, I'm going to say a little bit to you about what's going on in the last 3, but you won't see me calculating anything by hand. All right? What I would like to do before I go to the next, well, I'm going to back up and go to the chapter, is I want to come to this right here. And look, I know we haven't done problem 6. We can't do it yet. But the bonus problem is actually a proportion problem. One of the things I want to warn you about what we've done tonight is if you see me say anything about any of the problems I did, and I did one of each type for you, from start to finish, and said everything I could say about them. Did you see me say anything about a sample mean, a population mean, about a mu or an x bar? It was all about a percentage or a proportion, right? That's how you know what you're looking at. Because now you have 2. Right? You have the stuff about confidence interval and test of significance for a population mean, where sigma is known. And then you have this confidence interval, test of significance for a population proportion. And obviously, the standard deviation is not known over here, but that's all that estimating I was doing, even making a guess, right? So this bonus problem here is a proportion problem. Look, you got to get this in your head. I mean, I'm not keep telling you this just for my health. Mu, trying to say something about mu, you know sigma. Here's your set of stuff. You're talking about a population proportion. You're trying to estimate it, do claims about it. Here's your set of stuff. My next chapter that I'm going to do, we no longer know sigma, but you're trying to do. There's 3 sets. You got to know which one's which. That's trying to help you pick out what you're trying to do. All right? So let's go back to this bonus problem. It says, question 11 on the fall 2015 Math 1530 asked, if you had to lose one of your senses, which would you choose? An active online survey website suggests that the majority of people say they choose to lose their sense of smell. The sample size was 4,729, and then looks like a majority means more than 50%, right? It is the same true for the population of all U.S. college and university students. It says, create an appropriate graph to display the distribution of senses and insert it here. What type of variable is senses? You know, you're going to lose this sense. What type of variable is that? Is that categorical or quantitative? That's categorical. What's your choices here for a graph? It's either a bar graph or a pie chart. So I come over here. I've got Minitab up for you. Graph, bar chart, because that's just me. Leave that alone. You're looking at the raw data. I want a simple one. I'm going to put in here, what was it, census? Census, and I would appreciate it if you would show me the bars in terms of a percent. That's just me. I like to look at it like that. All right? I click OK. I click OK. There's your graph. It looks like definitely in our sample, what did they prefer to lose? What did they choose to lose? They chose to lose smell. What ones didn't they want to lose? They didn't want to lose their hearing or their seeing. They could deal with losing their smell, right? So what's the most likely choice here? The most likely choice was smell. What's the least likely choices? Look, I picked hearing and seeing because they're about exactly the same, right? Okay? Those are the smallest ones. That's your graph. It says, how many of the students surveyed said smell? Here's the way you do that. Stat tables. We want it to count things up for us. I want to tally individual variables. That was stat tables, tally individual variables. What variable do you want to tally? Census. Look, you can do counts, percents, all that stuff. I just want counts here for a moment. I want to tell me how many said smell, how many said hearing, how many said seeing. I click OK. There's your table. 40 said hearing, 36 said seeing, 504 said smell, 132 said taste, 102 said touch, out of 814. Copy, paste. All right? So what it was asking you for was how many said smell. How many said smell? Looks like 504 to me. Copy that table and put it there for me. What proportion of our sample said smell? Well, dear God, I know it was 504 divided by 814, right? Yeah? Hang on. We're doing the software. I'm not going to pull a calculator out. Stat, tables, that's the same place I just was. Variable census, put percents. It'll tell you the percent out of each one of those categories out of the total. Right? And actually, if you want to be nice, just give me this one right there and tell me that you're reading off of that for both of them, right? The count, how many said smell, and then what the percent was. 4.91% said hearing, 4.42% said seeing, 61.92% said smell. Give me that table. Just give it to me once. The count's 504. Hell, the percent, the proportion is 61.92%. The proportion is 0.6192. Okay. Assume for the purposes of this problem that we may treat the fall 2015 sample of Math 1530 students as a simple random sample from the population of all U.S. college universities. Why we want to do that? What was the first one on all these? You needed a simple random sample. So we're going to assume this is a simple random sample. Use Minitab to calculate a 95% confidence interval for the proportion of students in the population that would choose smell to the survey question based on our sample data. Copy and paste the Minitab output here. Okay. We go to stat, basic statistics. Everybody see where there's all this display, store, one sample Z, one sample T, one proportion, all that? I want a one proportion problem here, right? There's one proportion, there's one population, there's one sample. I'm going to one proportion. The little drop-down menu here says one or more samples each in a column. No, I got one sample in a single column, so I got to deal with the summarized data here. The summarized data, it wants to know the number of events, the number of successes, and it wants the number of trials. How many of the students said smell? What was the number there? Oh, hell, it's looking right at me. 504. And the number of trials is the number in your sample size, right? It's your sample size, and your sample size here is, what is it? The total N is 814. You got to go to options to get the confidence interval. You can put any confidence level in there you want. The problem asks for 95%. And please do one thing for me, in case you might have screwed something up. Make sure that this alternative hypothesis is not equal to. You know there's three under here, right? Less than, not equal to, greater than. The three choices are alternative. The method is exact. I know we can do approximation. Hell, I want exact. I'm going to click OK. OK. Your 95% confidence interval is 0.584 to 0.653. Excuse me, that's 0.585 to 0.653. That's your confidence interval. Remember, we're doing Minitab to do this. You didn't have to calculate it by hand here. You use Minitab. I got the exact answer here. Now, coming back here, it says copy and paste. You're going to copy that, highlight it, copy it, paste it right over there. Boom, I can see it. There it is. It says, interpret the confidence interval you just reported. What are we trying to estimate? The proportion of all U.S. college and university students that would say they would lose smell. What do we know? We are 95% confident that the true proportion of university and college students that would choose smell is between 0.585 and 0.653. If you want to give it to me in percentages, with 95% confidence, the true percentage of university and college students that would say smell, would answer the question to say smell, is between 58.5% and 65.3%. It's the same interpretation. Minitab did the work for you. All right? Now, one more. What do you think about the next thing? Do our results contradict the results obtained from the survey, or do they appear to agree with it? Explain. So, I mean, it's a yes or no, right? Either they agree with the survey, the website, or they don't agree. Well, I don't even know what the hell the site said. It says, suggests that the majority of people say that they choose to lose their sense of smell. What's the majority mean? Majority means greater than 50%, yeah? Agreed? Majority means that the website's trying to tell you that it looks like it's greater than 50% of the people would say, university and college students would say, or people would say they would lose smell. Does our confidence interval confirm that or not? They're asking you about a test of significance without asking you. Right? See, the website's suggesting that the majority would say smell, greater than 50%. Anybody remember my little story on Thursday? The connection between a two-sided test and a confidence interval? If the value that shows up in the null is in the confidence interval, you do not reject. If it's not in the null, you reject. Remember that? See, I'm going to do this. What they're asking you is to do this. And the way our question is worded, I'm going to give you, because they're asking about the confidence interval. They didn't tell you to do the test, right? They're saying, looking at the confidence interval that you just gave me, does that little confidence interval support what the website says? Does it agree with it, or does it disagree with it? So my question is, what are we going to do here? You see that value? Is it in the confidence interval or not? .5 is not between 0.583 and point whatever in the hell the other number was. It's not in there. What do you want to do? Yeah? It's not in there, right? That value's not in there. You reject the null hypothesis. You favor the alternative. So what's our data telling us? Our data is not picking a side, because I'm giving you a two-sided test here, right? It's trying to tell you that the percentage, or the proportion of university and college students based off of our sample that would say smell is different from 50%. Yeah? And actually, ours is actually suggesting it is greater than 50%. Our sample, our data is confirming. It's agreeing with the website. That's it. There's nothing else special. And that's what it's asking you, does it? What do you think? Well, hell yes, it does. My little, if I did a two-sided test, that little p.5 is not in the interval. It's trying, my data, our data is trying to tell you that we want to favor the alternative, right? That the proportion of college and university students that would say smell is different from 50%. Well, different from 50% means, the way we're looking at it, greater than 50%. It's agreeing with the website. you want to get real picky, and what should have happened here if I was writing this is I should have came over here and I should have went to stat basic statistics, one proportion. All this is the same, right? The number, all that. Perform a hypothesis test. The hypothesized proportion, that's the null right there. That's where you put the null in, right? And I click options. The website says it's greater than 50. The majority is greater than 50%, right? That's what majority means. So I don't want to do a two-sided test. I want to do a one-sided test. There should have been a part G and F, and we shouldn't have asked you frickin' part F. Sorry. And I should have clicked OK. I should have clicked OK, and it just did the test for you. It gives you a p-value of 0. When you get a p-value of 0, what do you want to do? I want to reject the null hypothesis in favor of the alternative. What's our data telling us? That the proportion of college and university students is that would say smell is greater than 50%. That's the right way to do the problem. Do our result, look, if they'd have told me it was different from 50% up here, I'd have done a two-sided test. No, hell, it says suggests a majority. It's telling me it's greater than. That's what should have happened there. You're going to want to do this for me, and then we'll all be happy. Do that. Tell me that. Yeah. It confirms it. It says it's different than 50%. Everybody will be happy. You get all the bonus points. Okay? Now, that brings us up to what? There's one problem left on your capstone. Right? You got 3 problems to do for homework over the weekend. Confidence interval, sample size, testing about a proportion. What I want to do is this. Yeah, I know I got 3 minutes left. Every minute's going to be important between now and when we are finished. Okay? So we're going to back up. I skipped over everything to get to this other last chapter there, chapter 22, because that was the last one where I did things by hand. Okay? So this chapter 20 is inference about a population mean. And you're supposed to tell me, dude, we already did that. Yeah, we did. But the difference is, so it's a population mean mu. Okay? That's what we did in 16 and 17, right? When they say inference, they mean confidence interval and they mean test of significance. Okay? So, we don't know sigma. These are inference methods for practical use, where you don't know mu and you don't know sigma. Now, the confidence intervals and test of significance, they're still based off of some sampling distribution. They're still based off of, we're still going to use X bar to estimate that's not going to change. My interpretation of the confidence interval, with 95% confidence or we are 90% confident, whatever, that's still the same. The interpretation of your p-value is still exactly the same. Okay? Now, the first thing is this. Conditions for these. Anybody know what number 1 is? Thank you. Finally somebody answered me. Number 2 is the population distribution. Where you're choosing your sample from? Before it had to be perfectly normal, right? It had to be normal. Somebody had to tell me that the population distribution was normal. Not anymore. It needs to be symmetric, single-peaked, unimodal. And I'm going to give you, obviously, the mean of the population, mu is not known, and sigma is unknown. All right? I mean, I can write that down as a condition, but shit, it ain't in the problem. It's not really a condition. Is mu and sigma are not known. Not a big deal. It's all fixable. I got 650. Y'all be careful going to the house. Don't fix my 3 homework problems. Everybody have a nice Thanksgiving, and we'll see you on Tuesday, right? All right, be careful. If you go shopping on Friday, especially be careful. Somebody gave me a word of advice once. If you see a crowd running at you, turn and run with it. Be careful.